Hello. No, I did not say anything yet. So we can start now. All right. Good morning. Do you have any questions before we start? Yeah, don't worry. I think I saw a video news of some professor from Singapore who lectured for 2 hours on mute before a student let him know. So yeah, I appreciate that you check. Always check. I don't want to lecture for the entire class with being on mute. That would be not funny. All right. Yeah, it happened. I don't know how it happened, but it did happen. So, okay. So, any question? All right. I'll take it that as a no. So, oops, give me a moment. All right. So last time we were discussing 10.8. Sorry, 10.7 method of moment estimators. Okay. So let's recall the idea. Okay. So the idea is basically you have two worlds. You have the population distribution, which we call, let's say, XP, all right? Usually we just call it X, but there's going to be a sampling distribution here, so we will just call it population distribution. So XP is your regular, right, model. This is your model, right, our model, like normal mu sigma square, uniform AB, that kind of thing, right? So it depends on parameters, right? It depends on unknown parameters. So XP depends on unknown parameters. But so for that reason, right, if you take the moment, right, the population moment, so basically, let me do the P as a subscript because I will take a power. Expectation, right, of XP raised to K, all right, where you can let K runs from 1 to etc. as far as you want, then you basically, these guys are functions of the unknown parameter. Right? For example, if we let the population distribution to be uniform AB, then expectation of XP is A plus B over 2, and expectation of XP squared will be B minus A squared over 12 plus A plus B squared over 4. Okay? So the point is, right, that when you take the moment of the population, you will get functions of the unknown parameters that you care for. All right, so the opposite side of thing is the so-called sampling distribution, all right? What you see from your sample, and it's going to be a little bit of an abstract framework, but it's just basically what we talked about last time anyway. Another term that you might hear is the empirical distribution, okay? Sampling empirical distribution, I will call it X sub S, okay? S for sampling. What is it? It's gonna be basically, right, our sample, but our sample viewed from this point of view. Basically, you should envision this as a random variable. What values does it take? It can take on any one of the observed value from your sample. x1 to xn. Notice I write here little x, okay? Because I mean for these as values. I don't mean for them as random variables, right? Notice a switch of context. In chapter 8, these guys are capital letters. The reason is I care for the randomness, the probabilistic properties of the statistics made out from these guys. Right now, what I'm caring about is how to estimate the parameters. So I switch the point of view to these being numbers, okay? But that's what I say was like, it's gonna be like hard or confusing about statistics is we will be very fluid in terms of switching the point of view between little x and big X, all right? Here, little x makes sense because I think of them as values that I will assign, right, to the estimators for A and B. Anyway, here I think of them as values that this random variable can take, and it take it, right, equally likely, 1 over n each. All right. The point of view here is very simple. Because we take an IID sequence, all right, any of the values we observed are as equally likely as any other value that can come up. All right, that's all. That's the 1 over n. It comes from the fact that because our sample is IID, any value we observed, right, will be as equally likely as any other. So these are observed values. All right. But from here, you can form the so-called, I will call it like this, all right, sampling distribution moments. I know last time I called them sample moments, but I realized that by doing that, I call it a sample variance, and it can cause confusion with the sample variance S squared that we referred to before. So I just call them sampling distribution something something. It's longer, but it's clear, right? It distinguishes it from the other one. So sampling distribution moments are basically the moments of this guy, all right? So it's very easy, right? For example, expectation of the sampling distribution to a k is the sum of xi raised to a k, right? Sum from 1 to n, everything divided by n. Okay. Is it clear on these basically two objects, two worlds that we're looking at, the population distribution and the sampling distribution? Each has their moment, right? The moment of the population depends on the unknown parameters. The moment of the sampling distribution depends on our observations of our sample. We know this, we don't know this. Okay, so what's the point? The point is, right, the method of moments is very intuitive. The method of moments say, equate these guys. Equate the sampling moment with the population moment and solve. And that's it. Okay, that's it. For example, right, we have talked about how we did this before. For example, suppose that we have IID exponential lambda. Then the method moment say, right, the population mean, but because exponential lambda has mean lambda, right? So lambda is equal to the, sorry, here, right, equals to the sample, equal to the sampling distribution first moment, but that's just, you know, a fancy word for sample mean. So lambda hat is equal to x bar. All right. Well, we can do a bunch of other examples of this type, but right, let's do some remarks, and then we do more interesting example. So remarks about this, right? The first remarks is pretty obvious, is how many equations? In other words, how many k's? Right? The method moment just say you equate this. right? For any k, that's relevant. But how many k's will you put in here? How many equations will you put in here? How many moments will you match up? So the answer, right, is equal to number of unknown parameters. Correct. How many unknown parameters do you have? Exactly. Equal to the numbers of unknown parameters. So, right, so you see here we have one unknown parameter, so we only need one equation. And of course, right, the equation should run from lower order to higher order. Okay, I know one equation, but you shouldn't pick the fifth moment, for example, here. And I'll explain that. Actually, if you think of that, then, right, so first of all, right, there's one parameter, so one equation. So for normal mu sigma squared, right, for example, these guys have two unknown parameters. So you can expect two equations, all right? Two equations involving the first and second moment. And the method moments, right, conventionally always go from first order to second order, etc. Okay? So conventionally, or I don't know, right? It's just the way things work. We go from first to second, etc. Right? The reason is this: if you don't kind of follow this convention, you may see some confusion or some other alternatives like this. For example, let's take our exponential, right? Or actually, you know what? Let's take the Poisson, okay? Let's take the Poisson. Okay. Now, so XP, right, is our population distribution. Basically, it's just a generic name for the Poisson. What is the expectation of this guy? What's the expectation of a Poisson? Lambda. What's the variance of Poisson? Yes, also lambda, correct. So therefore, right, so suppose you use, so basically what is expectation of Poisson square? It will be, you know what, I regret, I regret. Sorry, you know what, I want to do something easy, that's all. Let me switch back to exponential, all right? Then variance of the exponential will be lambda square. Is that okay? I'll explain. It's just some technical stuff. I just want to make it easy for you to see, right? If it's exponential, then variance is lambda square, all right? So what is the expectation of exponential square? It's clear that's going to be 2 lambda square, right? So now, if you were to use the first moment, you equate, right? If you use the first moment, then you will get lambda hat to be x bar, right? Because you would do this equal to first sample moment. But if you were to use the second moment, you will get 2, right, lambda square to be sum of xi square over n. Yes. So you will get lambda hat to be, I guess, right, sum of xi square over 2n square root. Is it okay? So first, are these the same? Are these the same statistic, same estimator? The answer is no, right? They're different numbers. Second, are they valid? Do they both make sense? I think they both make sense. Okay, they both make sense as estimators for lambda. But which one is a method of moment estimator? Which one is a method of moment estimator? This one. Okay. And again, it just comes from convention. You start with the first moment first. If you have the answer there, you stop. You don't go to a second moment. Is that okay? Is it okay? So, right. So I explained this so that you understand, right? That's how the method, how the convention works, right? This makes sense. Actually, you could look at this as an estimator, but conventionally you would not call this a method moment estimator for lambda in this case. That's all. It's an estimator. It's just not method moment. Question. Okay, so the second remarks is this, that so usually, right, usually most of the case we'll see k equals to 2, right? I mean, there's k equals to 1 as well, but I mean, we'll talk about k equals to 2, right? So there are two parameters to estimate. So that means that you do two equations, right? You do the first moment to be the sample mean, the second population moment to be the sample, the sampling distribution second moment, let's say that, right? Okay. Now, what I want to say is this, right? Nothing. My message is this. My message is if you use the second moment philosophy, meaning if you equate the population second moment with the sampling second moment, sampling distribution second moment, then you get this estimator for lambda. All right. My point being is this estimator for lambda is not the same as this estimator for lambda. So you get two different estimators. Is that clear? Now, of course, if you come up with this, you and your friend, right, would say, okay, so which one is the method of moment estimator, right? Because say I ask you to find the method of moment estimator, you come up with this, your friend come up with this, who is right? Do you understand? My point is, then this person is right. Not that because this person did something nonsense, it's just you wouldn't call this method of moment estimator. That's all. I mean, it's not wrong in any fundamental way. It's just this is not designated with that name. Okay? Your question is very strange. Sample and population moments are always different because one is on a sample side, one is on a population side. Say your question again. And the point is both of these are lambda hat, okay? There's nothing sacred about lambda hat. They're both possibilities for lambda hat, or if you want, I can call this lambda hat 1, lambda hat 2 to distinguish them. Hat just means estimator. Hat just means estimator, right? So they're both possibilities for lambda. Yeah, I mean, again, right, it goes back to what I say before, that when you say lambda hat, is there any God-given reason that there's only one answer there? No, right? Because anyone has their right to guess what lambda hat is, okay? The real question is, what's the quality of the lambda hat that we come up with, which we did not discuss, right? But then we come up with, right, the idea of there's a method that will come up with a particular lambda hat. Is unique in that way. Like this is like a name for the method, a name for an estimator. So I'm explaining that if you were to use this method, then X bar is, in this case, right, is the method moment estimator. Because the point is, do you see that here this person is also using the moment philosophy, okay? But that person just go with the second moment, skipping the first moment. So the point being is, right, that we don't call this method moment estimator. It's still an estimator. All right, so think about it. It is simpler than it is. You can just really ignore this if you want. But I have seen people making this mistake or getting confused conceptually on why we don't go here. And I just want to bring it up. All right, so back to the second remarks that, right, usually you have two unknown parameters, so you make two equations out of it. And the method moment usually tells you something like this, okay? But it usually, right, this equation is usually awkward in this way. A better way to write this system is this. Okay. So first of all, I claim that these two systems are equivalent. I'll explain. Second, I claim that this system is easier to use, okay? For k equals to 2, or for that matter, actually for higher k2. So first of all, why are they equivalent? Well, they're equivalent because you can transform one to the other, right? Because, of course, the variance is expectation of the square minus the square of the expectation. How about this, right? This requires us to do sum of xi square over n, right, minus x bar square is equal to sum of xi minus x bar square over n. Well, you can run some algebra to check this, or you just have to realize that here is nothing but the variance of xs, because, right, this is exactly expectation of xs square minus expectation square of xs, and this is variance of xs. So of course they're equal, okay? Xs being the sampling distribution I discussed above. In other words, this random variable that takes on the values of the sample with 1 over n probability each. Okay. So the point being, though, right, is that the method of moment force you to use the S prime version, okay, for the variance rather than the S version, S square version. That's the point. But using this system is easier because most distribution, you learn the variance of the distribution, right? Like Poisson has variance lambda. Most people don't remember what the expectation of Poisson square is. They deduce it, right? Same as, let's say, normal. You know the variance of normal sigma square. You have to deduce expectation of normal square from it, right? So this system is easier to use, and we will use this, right, for method moments of, like when you involve two parameters, or for that matter, most of them, because the variance is given. This is much more convenient to use, even though, right, the language of method moments is stated in this way. Any question on this? So for example, right, if you have x1 up to xn, iid normal mu sigma square. Then using the method of moments, right, you see that mu, right, is x bar, or so then we can just do mu hat, right? Then we got variance of xp, which is sigma square, is equal to s prime square. So we can also throw a hat in there. That's it. The equation is already solved for us. We got the estimator directly out of that. No need to solve any equation, right? Any question? But of course, notice, right? Again, the difference is if you use the method moment. So here, there's that kind of contractual, right? Contractual language here. You say you use the method moment, so you cannot write s squared here, right? Now, of course, like I said, there's nothing wrong with from here. Then you say, okay, let me use s squared. But what happens there is you use a different estimator, okay? Which is perfectly fine. There's nothing wrong with that. But you don't get to call this the method moment estimator. That's all. Because method moment estimator will be this. So that's a unique identification that way. Okay? Any question? Okay, so let's see one case where we get to solve some equation. This is the case where, let's say, take uniform AB. Okay? So what do we have, right? So when we can solve for solution, then we just put a hat on them, right? When we do not solve for solution yet, let's just not write a hat on. What do I mean by that, right? So the system says, right, equate population mean with sample mean. So we got a plus b over 2 will become x bar. That's the first system. That's the first equation. The second equation says, let the population variance be the sampling distribution variance. That's the second equation. Okay? So from this equation, you're supposed to solve for A and B, and you call them A hat and B hat. Okay? So let's solve for them. Well, how do we solve for them, right? Again, who knows, right? Depends on how the variance and the expectation and variance, right, got interacted with the parameters, right? Who knows what kind of equation you get. Sometimes most of the time it should be easy, but sometimes, right, you just have to solve some system. So here, it's just some trick that you observe. So for example, a plus b is 2x bar. Here, right, b minus a times b plus a is 12s prime square. All right. So obviously, right, if you x bar is non-zero, you divide, then you got a plus b is 2x bar, b minus a is 12s prime square over 2x bar. So I guess that becomes 6, right, x bar. Right? And then that means b, right, oops. That means b is 1/2 of 2x bar plus 6s prime square over x bar. A will be 1/2 of 2x bar minus 6s prime square over x bar. That's A hat. Any question? So this, right, if you follow the method of moments, you get these estimators for A hat and B hat in a uniform. question? So, all right. So that's just the method, right? You can do the calculation. But now let's take a step back and observe what you get. Does this seem to make sense? Because a method, right? I mean, a method, you follow it, you get something. But you still want to kind of see, okay, does the formula make sense? What am I getting? Does it seem like anything? And B, does it seem unusual, or does it seem like what you not anticipate, right? For example, suppose you have uniform AB. What is the natural estimator for A hat and B hat, for A and B? What's our natural estimator for A and B? Yeah, with the one, right? I mean, with the parentheses. I know you can't write that on the chat, but yes, you're right. It just have to remember that, right? The min, the max. Very good, right? So first of all, the method moments do not give us the order statistics. Okay, it gives us something entirely different. All right. So that's new, right? So this is something where I guess one thing that you may become disappointed, or you're like, okay, what's new from what the example we've done so far is because, right, you got lambda had to be x bar, mu had to be x bar. There's some slight change, but nothing dramatic. Okay. But with the uniform, you see, right, these guys are very different from the order statistics. So that's probably the first place where you see is a big difference from what we would think of as the natural estimator from this. But okay, so now go back to here. Can you see this formula as making sense, or it's just complete, symbols mixing together and just throw at you? Can anyone make sense out of A hat, B hat for the method moment? So, right, sure. So the method, all right, Christine, the method stops at the moment that I can write down the equations. I mean, I guess it doesn't stop, but that's all it tells you. It tells you how to write down the system. After that, it's up to you to solve. Okay. So again, but how do you write down the equation? Same thing. Equate population mean with sample mean, population variance with sampling distribution variance. And that's it. And then you plug in what you're supposed to. Oh, okay, hold on. Christine, are you okay with that? So as long as you see how I get the system, the rest are algebra. The rest is not something statistics responsible for. Okay. So I guess maybe I'm not sure your question's along the line of Madhav, but again, right? This is where trick of the trade comes in. It's just how you pick up skills from different things. But I mean, right? If you ever take linear algebra, right? This gotta draw your interest. Why? Because oh, you know what? I'm so not awake. I did something wrong here. It's b minus a squared. It's not b squared minus a squared. I so apologize. So here I should do something like this. Sorry. What I'm saying is like you gotta pay in. You gotta see the b minus a. So here, so I guess thank you for asking question. It should be this. It should be this. All right. But the point being is when you see a plus b, a minus b, you just pay attention to, right, how to reduce it down to a linear system. So this is nonsense. But right, this being a linear system of b minus ab plus a, well, then b is just this plus this over 2, and a is just this minus this over 2, right? So the mistake I made, I do the right method. The mistake I made is I just was not awake. I look at something differently. So like that. Is that okay? Because right, b is this plus this over 2 because the a cancel. A is this minus this over 2. Right? Is that clear now? Yeah, well, thank you for asking the question. Otherwise, I would not be even noticed that I made a mistake. Christine, you're good? All right, so now my question is, can you make sense out of this? What does it try to tell you? Like, I hope everyone see why we use the min and max for A and B. Why would you use something like this for A and B? A hat, B hat. So why uniform leads to that? I mean, I know, right? It's method moments, but you're not making sense out of it. Meaning, like, I'm asking you, what's the intuition? Do you see any structure here? Okay, maybe this is not something you're used to. Let me tell you, right? Well, if you try to simplify this, you got x bar plus square root of 3 s prime, x bar minus square root of 3 s prime. Does it seem any better? Still no. All right. So let's take A and B, right? Uniform. So you have your sample, right? Somewhere in here, because it's a random sample. What does the method moments tell you? It tells you, right? Start with x bar somewhere here. What do? You go to the right, worth of exactly. It just formed exactly an interval around the mean. With what kind of with what kind of width? The width is s prime, right? I mean, the unit, and the length, the number of steps is square root of 3. Now I'm sure, right? Well, sure. I hope everyone in this business have seen something like this. Okay, even if you took some elementary calculus, statistic, you've seen something like this, confidence interval, right? So, well, you're witnessing some confidence interval right here, right? This left and right, S, right now you see the meaning of the standard deviation, right? This is a sampling distribution standard deviation. It just measures the spread. And then, right, from there, square root of 3 is probably that kind of score, right? That corresponds for the uniform that hopefully you cover the reasonable range of the uniform. Yes. But why does the method moments land you on this weird form? It's not that weird, actually, it's very natural, because method moments, by definition, only allows you access to moments to construct parameters, to construct estimators. So of course, it has to rely on the mean, has to rely on the standard deviation to construct. And what's the best way to construct A and B? Left and right. Yes. So this actually completely makes sense. It's just a different approach to the min and max. Any question? Yeah, okay. Now let's not read too much into it, all right? Uh, now I would quote Derek, where I say, this is what method moments tells you, right? I'm just interpreting what it's trying to do intuitively. But I'm not saying like based on symmetry, the method moments work like this. Or I would say the method moments reflect symmetry. You understand what I'm trying to say? There's no causation here. That because of symmetry, it does this. But I don't know that far, right? I just say that, yeah, it's uniform. It's uniform. But what I'm trying to say, right, is that with the uniform, you are estimating the beginning and the end of the distribution, right? And the method moments give you some kind of interval centered around the mean with the left and right approach, rather than going directly for the min to max. Okay. And again, let's not be too dramatic about this. My point being is, right, when you read this, I hope it comes alive to you as more than just symbols. That's all I'm trying to say, right? However you want to read into it, that's not my responsibility, right? But what I'm trying to say is this has meaning. It's not just some random matchup of symbols that will spit out A hat, B hat. Okay. Any other question? All right. So just one more remarks. This one is actually a little bit not our responsibility so much, but these remarks will be um, you can generalize this, okay? This philosophy can be generalized to other, let's say, quantities. So the philosophy is you just do population something will be equate to sampling distribution something. That's it. That something is up to you. Can you think of something else that, um, you know, that we actually, right? So how to say this? If you apply this philosophy, right? So how would this work? For example, yeah, maybe can you think of something that would lead to this? So basically what I'm trying to say is, right, the philosophy behind the method moments is kind of the intuitive reason why we have chosen estimators so far. Okay. But of course, right, the method moments would limit this to only equating moments. That's method moments. But if you use this philosophy, there's no reason why you have to restrict yourself to method moments. You just cannot call it method moments anymore, right? For example, you could say the population or the stats, or no, right? Basically, you can say population max is equals to sample max. Population min equals to sample min. And if you do this, what do you get? You get this, right? You can also do population median equal to sample median. Okay? Population quantile equals to sample quantile. Now, like I said, right, it's a philosophy, meaning it's a principle, if you will, right? Maybe philosophy is such a heavy word. This principle, meaning equate the population with a sample. But of course, right, the method moment just restrict itself to moments, and that's enough. I mean, why? That's what they want to do. But if you go out of that, right, you can pick your estimators in many other ways. Okay. Any question? So now let's move on to the second method, which is maximum likelihood. All right. And this MLE will be very, very popular. Okay, you will see it in any all statistics class going forward if you take all the statistic courses. So because of that, right? Sorry. So because of that, is called MLE, right? MLE is the abbreviation for maximum likelihood estimators, right? We use it that often. All right. So how to do this method? So first, there's a concept of likelihood that we want to discuss. Likelihood function of a sample. Okay. So suppose that you have a x1 up to xn random sample. And this concept is very, very general. It doesn't have to be IID, whatever. We'll see how it affects how the ID comes in. But the likelihood function of the sample, okay? So the likelihood function let us denote it for now, right, by L, will be a function of, let's say, little x1, little x2, little xn, all right? Notice how I write little and not big X. Tells us how likely it is that we observe this particular sample. Okay. So for example, like basically, I mean, we do this all the time. Suppose you roll a die 10 times and you observe like, all sixes, for example, right? You might think, wow, that's rare or something, right? So basically, given a particular values of the sample, right? A particular realization of the sample, the likelihood function tells you, okay, based on your model, how likely it is that we'll observe this particular coming out of a sample. Okay. So now let's be concrete. For example, let's say x1 up to xn, let's say IID, Poisson lambda. Okay. What's the likelihood function in this case? Well, now, right, because we have many x's that we carry around, I would use this notation, right? Vector x standing for x1 up to xn, okay? The tuple. So the likelihood function will be a function of these values and lambda 2, right? It will be a function of these two. It will be a function of the sample values and the parameter. Well, what would it be? How likely in this case is just probability, right? It's just a probability of the first sample taking on x1, second sample, right? Sorry, not second sample, second trial, right? Second experiment, whatever, like that. Okay. Yes, but x is a vector that represents my sample values. I don't want to keep writing x1 up to xn, so I just write x with it. Okay. All right, so I hope you see, right? This reflects how likely it is that we observe x1, x2 up to xn. All right, little x. This just tells you the probability, okay? And the reason why we multiply them together is because they are independent, right? That's the first I. Now, of course, now we'll use the second I. The second I says that they are all identical, right? They're all identical, meaning all these probability are the same. So actually, I could just reduce it down to a single one. Like this, okay? Where x is a Poisson lambda. X now is our population distribution, right? There's no sampling distribution, so I just write x rather than xp. Is this okay? The last step is to write down specifically what this is. It will be a product of e to the minus lambda, lambda to the xi over xi factorial. There could be some cleaning up. Like that. Okay. Any question? So actually, you see, the likelihood function here is nothing but this is just the joint distribution of x1, sorry, big X. That's all, right? But here, I guess in statistics, in probability, we call it the joint distribution. In statistics, we call it the likelihood function. Is that okay? All right, let's look at another example. Let's suppose x1 up to xn, IID Bernoulli. Okay. So what is the likelihood function here? The likelihood function, okay, will be the probability, right, that you observe these values. Well, because they are Bernoulli, right, to remind you, Bernoulli random variable takes on two values, 1 and 0, with probability p and 1 minus p each. So the xi's here, right, will be just 1 or 0s. And so it will be a product, because they're independent, okay, of individual probabilities. What are the individual probabilities? They are p and 1 minus p, right? It's going to be p if xi is a success. It's going to be 1 minus p if xi is a failure. So it will be p to the sum of xi, 1 minus p raised to the n minus sum of xi. Any question? So here, I would like to take a remark. Your text somehow does not like the Bernoulli. Your text likes binomial, all right? So first, let's ask you a question, right? Suppose you have x1, xn, IID Bernoulli like this. What is the sum of xi? When I sum independent Bernoullis, what do I get? Correct. It's going to be binomial, right? NP. So let's call this x. Your text would, instead of laying it out like this, they'll say, let x be binomial NP. And they will do likelihood function of x. Okay, it's okay. But for me, a experiment should have n random variables, at least for the class. So somehow when you switch to one single random variable, for me it's just a break of context. So I will stick with this. But let me explain to you, right? For the textbook, they will do something like this. Likelihood function now is a value of one single x, right? Because there's no, there's no vector here. And what would be? It will be the probability you observe x in a binomial. So that will be n choose x, right? P to the x, 1 minus p to the n minus x. Right? So observe is exactly the same, right? If you replace the sum of xi with x, that's exactly what you get. Of course, right, I do know there's this term right here, but this term is independent of p. So from the likelihood function, point of view, even though I say, right, it's a function of these guys, eventually our point of view or our focus will be turned on the parameters. We think of these guys as fixed because it's a sample value, right? We already see it. This is the unknown, and we want to work with this. So from that point of view, right, because this is a constant, it's not depending on p, this likelihood function are equivalent in that sense. Is it okay? But when you see the text, right, do not be confused when they give you a binomial. You can feel free to convert it to IID Bernoulli. Actually, I will always present the right result in the Bernoulli context, and I will ask you questions on the exam with Bernoulli context. All right, I will not use this. So just so you know. Any question? Okay. So let's take another example. Right now, let's switch our point of view to the continuous. Right. Let's suppose you have x1 up to xn, IID exponential lambda. Well, so right, clearly here you still have, right, sample values. Of course, just because you sample from a continuous distribution, you still have values. But obviously here you cannot write something like this because it's continuous distribution, so you will get 0, right, if you calculate any kind of probability of a one single point. But the fix is easy, right? That's where likelihood comes in, I guess, right? Likelihood in this case is the density at that point. So the density here also plays a role of the likelihood, right? The density does tell you how likely it is that you observe a value around the neighborhood, right? If you're willing to go with that. For example, right, everyone would know, let's say a normal distribution, right, that because of the shape, you are more likely to observe values close to 0, right, rather than values far away. And what's the justification? Exactly because you use the height of the density, right, as your argument. A uniform, right, being a uniform because the height of the density is the same everywhere. An exponential, right, has value, right, has likelihood of values close to 0, and the likelihood of observing large values just decrease exponentially. So, right, that just says that the density serves as a perfect, right, measure of likelihood. It's just not probability, but when you talk about likelihood, it works. So in that sense, right, the likelihood function for the continuous context right, would be just the product of the densities evaluate at these points Is that okay? And that would be 1 over lambda to the n e to a minus sum of xi over lambda. Any question here? One more. Let's take the normal. Likelihood function based on the sample and the parameters will be 1 over square root of 2 pi sigma square e to a minus xi minus mu square over 2 sigma square, which in turn will be 1 over 2 pi sigma square raised to the n over 2 e to the minus sum xi minus mu square over 2 sigma square. Is that okay? So, right, again, likelihood function here is a glorious name for joint density. We're okay? Okay, so what does the MLE method do? All right, so the MLE method, the principle of it is like this. For any sample, right, for any sample, you have the likelihood function as a function of the sample and the unknown parameters. Okay, and here I put theta vector because, right, it could be more than one parameters, like mu and sigma squared, right? So here, mu and sigma squared together would be my vector theta, all right? So the point of view of likelihood function, right, is that you treat this as fixed. You've seen it, you know, they're constants. All right, so this is one of the points where, again, right, you treat the sample values as constants, all right? But again, I hope you see the context. The reason is because we are looking at estimators, okay? We use the sample values to estimate the parameters. That's why we can think of the sample values as constants. But when we want to understand how, right, these estimators fluctuate as you resample, then you must treat them as random, okay? Anyway, so here you take them as fixed. But if you take them as fixed, then this guy will be unknown, right? The unknown variable. Right. So what do? Well, you say, right, I have a freedom to choose anything here. Yes. For each value of the theta vector here I choose, I will have different likelihood function. Agree? For different value of mu sigma square, I have different readout in numerical value. Well, what do I choose? The answer for the MLE method will be, the MLE estimators will be the maximum or the maximizer, right, is the maximizer of Lx theta in terms of theta. Is this clear? So in other words, right, notice, I hope you have seen this notation before. If not, then pay attention. It's not max, all right? People usually read this as max. When you say max, you're looking at the max of the function. When you say argmax, you're looking for the argument that maximizes a function, okay? So obviously, so that's called a maximizer, all right? You're looking for the maximizer of the function. So basically, again, in English, you just choose a value of theta or the vector of theta that makes, right, this function maximize, okay? Any question? All right. So how to carry this out in practice, right? How to carry this out. So usually it's a calculus exercise. With some really noteworthy exceptions that we'll talk about, okay? With noteworthy exceptions. It's really not exceptions, it's really the norm too. But I don't know if you pay attention to the calculus rules to kind of see that is actually also a rule of calculus. We'll go over it, okay? So let's just do a concrete example. So first of all, actually, yeah, there's one more step before we can do this. So one more thing. So let's look at the example. Let's say x1 up to xn. Let's say IID exponential lambda. All right. We have said that the likelihood function will be a product, right? 1 over lambda e to the minus xi over lambda, which turns to 1 over lambda to the n e to the minus sum of xi over lambda. So the goal, right, is to find lambda that maximizes this function. The blunt response is just differentiate and set equal to 0. Okay, that's why I say usually it's a calculus exercise. But you not necessarily want to differentiate this function per se, because you're not trying to find the maximum of the function, you're trying to find the maximizer. Okay, so a very routine observation in this business is the maximizer of the function is equal to the maximizer of the log. Okay. Notice I'm not saying the max are equal. I'm saying the maximizer, meaning whichever value of lambda that maximizes this function, it will also maximize the log. Why? Because the log is a increasing function. Okay. So, right, if you have an x that makes the function higher, they also make the log higher, and vice versa. And so that's why, right, the maximizers are the same. Actually, this principle works for any increasing function, okay, not just the log. Why log? Because a lot of times we have a product structure, okay, for our likelihood function from the independence. So the log turns the product into a sum, and you love differentiate with a sum because differentiating works very well with sum. All right, so that's why log is a routine business, right? And you will hear the term log likelihood function. So in fact, right, the term L here will denote the log likelihood rather than the likelihood. Okay, here I just use L as likelihood because I have to introduce likelihood function to you first. But in a lot of textbook, when you read L, actually they mean log likelihood, taking the log already, not just likelihood. Okay, any question? So the business then, right, is to write down the likelihood function, take the log, so that would be, right, minus n log lambda minus sum of xi over lambda. All right. Then the next order of business is you want to maximize this, right? Let's find critical values. And by critical values, I mean exactly the same kind of critical values they taught you in calculus 1. Okay, so critical values, you take the derivative. Okay, and you set equal to 0, among other things. So here you do this, and you get this, you set equal to 0. Okay. So first of all, your critical value in this case, I hope you see, is x bar. Okay. Now, a very, very usual or very, how to say this, traditional jump is you just do lambda hat equals to x bar. Okay. But let me ask, what's missing? What's missing from, I hope you see, right? The solution here is really x bar, right? The solution for lambda is x bar. Just turn it over, divide by n. But anything missing? Is there anything missing when we jump to the conclusion like this? Is there anything missing? The thing that is missing is, how do you know this is the max? Okay, because I hope that the whole point of your education in calculus is that anytime, just because you found something, right, whose derivative is equal to 0 doesn't mean that it's max min. It could be either, right, like this. The cube function, right, derivative at 0, 0, that's neither max or min. In our case, right, it could be that, or it could be something more hilarious in the sense that, right, you solve for the critical value, it could be the min, right? And then you don't want to call this max likelihood function. Okay, so I hope you see that just because you solve for this doesn't mean that it's the max likelihood. It's the maximizer of this. All right, but I just want to make a remark that, so basically, if you want to carry out this routine rigorously, you need to take the second derivative and show that the second derivative is negative, right, at that point. Okay, so that you are sure it's the max. A lot of the times that step is skipped because a lot of densities, a lot of family behave in a very nice way. So the moment you solve for this, you automatically can be sure that is the, or you can just trust that it will land you on the max rather than otherwise. Okay, but like I said, right, this procedure in principle cannot be skipped. Whenever you solve for a critical value, you must check that it's the max, min, or neither. Okay, but for most of our routine calculations, you will always land on the max. So I skip this. No, Christine, you don't have to check. All right. Yes. No, you don't have to check. But there will be some other cases where you solve for this, you will land on the wrong answer anyway. I will tell you about that. Okay. So the what on the exam, that's where, so you don't have to run a second derivative test. All right. But there will be some cases where you solve for this, you get a wrong answer too. And then I will tell you about that. Okay. So yeah, no, you don't have to if you want a short answer. Okay. But pay attention, there's something else that's lurking behind the scene. That's what I want to tell you. So yeah, what Christine was asking is exactly what I would say next is, in this class, usually we'll just stop here, okay? Unless something else happens, which I'll tell you. But I want to warn you strongly that in practice, right, in real life, it's hard to tell, okay? Most of the time, people just go for this anyway. But I think a rough check always is recommended to see if this makes any sense, okay? Otherwise, like you may suffer the wrong result in real life without knowing it. Okay, let me solve for the routine cases, okay? And then we'll do the exceptional case next time. Another routine case will be, let's say, IID Bernoulli, okay? So remember the likelihood function as a function of P will be product, right? P to the xi, 1 minus P to the 1 minus xi, which will give you P to the sum, 1 minus P to the n minus the sum. Okay, then we take the log. To be, right, sum of xi times log plus n minus a sum times log of 1 minus P. Then we differentiate rather minus, right? And you set equal to 0. You multiply on both sides. Okay, and cancel the denominator. Clearly, let's see here, right, that this term and this term cancel. So you got NP is equal to sum of xi, or P hat is x bar. Any question? So far, notice, right, actually the answers are what we expected. Nothing unusual here, right? Nothing unusual here. So one last one, okay? X1, Xn, IID, normal mu sigma square. Likelihood function will be 1 over 2 pi sigma square raised to the n over 2 e to the minus sum xi minus mu square over 2 sigma square. Take the log minus n over 2 log of sigma square minus sum of xi minus mu square over 2 sigma square plus some constant. Where does a constant come from? The constant is that 2 pi thing, right? It's there, but you know what I'm going to do next. I will differentiate with respect to mu, okay, and set equal to 0. And pay attention. I will differentiate with respect to sigma square. All right. This may be a strange thing, but I do not differentiate with respect to sigma. I'm differentiating with respect to sigma square. Okay, because in a sense, I would look at the sigma square as the parameter rather than sigma as the parameter. Because you can imagine, right, differentiate with respect to sigma or sigma square may give you different answers in terms of the likelihood. Okay, so here I differentiate with respect to sigma square. That's the one point I want to emphasize. But either way, right, this constant would disappear. So I don't care to write down, right? It's 2 pi something. Who cares? They won't. The only term that plays, right? The players are here and here. Okay. So I will differentiate and set equal to 0 and solve for mu hat and sigma hat square. Okay. I will continue with this next time. All right. So yeah. Anyway, it's a good time to stop. All right, so if you have any questions, I'll answer. If not, I'll see you on Tuesday. Thank you. You too.
Professor?
Yep.
Our exam is like 2 weeks away, so I just had a question, like, is there gonna be a review sheet that you'll give us to like look over before, or just to re-look over the homeworks and quizzes?
So I can share the exam I have given in the past with the qualification that that does not reflect on what I will ask this time, or the kind of materials I covered in the last two times I taught might be, slightly different, from kind of materials I covered from this time. So that's what I can share, right? In terms of like concept and stuff like that, basically I will stop the materials 1 week before the exam, the Friday before the exam, and homework, quizzes, lecture notes, that kind of thing will be good review. And you can use the exam as a gauge on kind of the spirit of the questions I like to ask, you know.
Okay.
Yeah.
So we're gonna like basically like stop doing new things after next Friday, and then the
I
next
mean, I will still do new things. They're just not going to be on the exam, if that makes sense.
Oh, like right. Okay, so like the cutoff for the exam
Cut
for
off
material wise is
Friday.
next Friday.
So basically, the homework, right, of next week is still on the exam, right? You will turn them in, right on the exam day, for example, right?
Right.
So the TA will run a review session for you, right? I mean, he might have his own agenda. Um, they are like I would give out, right? I would share. I mean, I can share them today, the past exams that I give, so you can take a look. Yeah,
Oh yeah, that'd be awesome. Thanks.
yeah.
Professor? Um, so you said that the homeworks and the quizzes would be a good way to gauge what the exams would be like.
No, I did not say that. I say
Oh,
that
okay, I'm sorry.
the exam would be a good way. My past exam would be a good way to gauge my spirit, meaning the way I like to test, right? But
Right,
again, I'm if in case you want to, I mean, want me to be blunt, I'm not one of those professors who like to give you a review sheet where the exam is going to be a change of numbers from the review sheet. I want you to, absorb the material and show me that you understand, right? So that we tweak
right.
terms and that kind of thing.
Uh-huh.
But spiritually, in the sense that if you look at my past exam, you see the kind of topics I like to ask, the kind of concept I like to ask. Maybe, right? I tend to circle around that. In other words, I'm not going to ask some exotic topic, but my exam could be hard to some students because I do test you on your understanding, right? It's not like plug and chop where, okay, I remember this formula, I just blindly plug in, I get the answer, it must be correct, right? If you're not
Right.
aware of what you're doing, then I think my exam should not let you pass. But
Mhm.
like if you understand the concept, if you know the techniques, you can apply it. So in that sense, the quiz and the homework, right, I hope test you on your understanding, right? My exam will do the same thing. Like the
Right.
concept, I guarantee you, are not new concepts, but there are things like calculations, right? Your calculation skills, your calculus skills, that kind of thing that may come into play when the exam comes. Does that make sense? Plus,
Yeah, that makes sense. Professor, I think the reason I asked was because in some of the previous homeworks, there were like one or two problems that were kind of tricky and that did take a little bit of time. And
sure. Like
yeah.
so, I do know what problems you refer to, right?
Mhm.
So in that sense, that's why I would give the quizzes. The quiz might give you a better gauge of the style because the quiz is composed by me, right? So the homework is less similar to me. The quiz is more similar, but the
Mhm.
quiz also I designed them to be illustration of the lecture content too. So they're not necessarily just test you, right? They're more like illustration of lecture content. But the style or the kind of calculations I like you to do on quiz should carry over to the test a little bit in the sense that, like I like this kind of questions, if you understand what I'm trying to say, right?
Yeah, yeah.
So yeah, I mean, if you're concerned about the tricky question on the homework, I think like the central limit theorem type of questions. No, I'm not a big fan of them. I'm a big fan of fundamentals, right? Like statistics, sampling distributions, estimators, that kind of stuff. You must know, right? So 70% or 80% of the exam will be things I consider fundamentals. Meaning, if you don't know this topic, I don't think you have learned from my class. But like yeah, like central limit theorem, I don't think, right? I think I was pretty clear on what I think is fundamental and what's not in the course. So So you should explore stuff on your homework. That doesn't mean they'll show up on the exam.
Okay. Thanks a lot, Professor.
Sure.
Can I ask another question, but this time about the quiz?
Sure.
Okay. So for number, or I guess letter F, it
Yeah.
says use your answer in part E to find the density of the sample range R in this case.
Yeah.
Does that mean like to find the density of the exponential like we've been doing before?
The range is not an exponential, is it? How do you know? I mean, so from part E, you will get a joint density of the range and the min.
Yes.
Okay.
Yeah.
So let me ask you a simple probability question. If you get a joint of x and y, how do you get a margin of x?
Integrate the, oh, okay. So integrate the,
Usually, right now, over that's the universal answer. But sometimes, right, you always want to watch out for a special case in which x and y are.
independent.
Yeah, in that case, you get the answers for free. Now, I do not know, right? I have a slight suspicion that this is that, if you're lucky. But I don't want to say that, right? I haven't investigated the solution very carefully. So, but integration is always, right, the universal answer, right? Integrate out the other variables, you get a margin. But
Okay.
be on the lookout for the lucky time when you do get independence, all right? I have a slight suspicion that it is this, but I haven't checked my answer very carefully.
Oh, okay.
Does that make sense?
Yeah. Okay. I was a bit confused on that. Okay. Then I have to redo it.
Yeah.
All right. Thank you. Have a good weekend.
You too.